Okay, so let's first talk about the first problem. This problem gives you two strings S and T, and both are 0, 1 strings, and both of length n. And given an integer k, and each move you can swap Sn and Sj if the distance of I and j is less than k. Now you need to find the minimum number of moves to make S equals to T. So for example, if S is 1, 1, 0, 0, 0, and T is 0, 0, 0, 1, 1, and K is equals to 2, and you can get S to T by three moves, the three swap. The first swap is this, and then this. Yeah. And to solve this problem, first, let's make observation. And if we denote sum I to mean the number of the one in S1 to I minus the number of one in T1 to I, then at some conditions that sum I is equal to 0, we can split the problem into two parts. We can split this problem into two parts of first 1 to I and then I plus 1 to the length of S. So for example, if S is equals to 0, 0, 1, 1, 1, 0, 0, and T is equals to 1, 1, 0, 0, 0, 0, 1. And we can find out that at these positions, sum I is equals to 0. And we can split this problem into the first half and the second half. And why this is true? Because if at some positions, there are some swap that is from the left part to the right part and across the splitting line. And then this means that there must be another swap from right to left of this one, and they are crossed. So in this case, it is always better to make the left one to go these positions and make the right one to these positions to avoid the cross. And it turns out that they do not swap across the splitting line. And what is the benefit of this? It is that after we do this splitting of problems, then in each part, the one in S is either or to the right of the one in T in the corresponding positions, or the one in S is to the left of the one in T. So what we can do is, since that the swap operation is reversible, we can always think that the one in S is to the left of one in T. If it is not, then we just swap S and T. Okay, now after this observation, we turn this problem into an easier part, and at each subproblems, we have all the S in one that is to the left of one in T. And then comes to a very magic part, is that we can turn 1 to n positions into k times n over k grid. For example, if n is equals to 20 and k is equals to 5, then we can turn this into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12, 15. Yeah. And let's mark each positions of one in S to be red. For example, this can be red and this can be red. And then we mark all the position ET to be yellow. For example, this is yellow and this is yellow. And after this representation, we'll find out that every time if we change our positions, for example, this 8, if we swap these positions to the right upper quarter, then the cost should be delta x. You can check it. And if we swap this 8 to the right lower quarter, then the cost should be delta x plus 1. And we will not swap the 8 to the left part, either left upper or left lower, because we already, in this observation, we already know that all the 1 in S is at the left of 1 in T. So we will only swap it to the position that has a bigger number. Else, then there must be a cross like this. There must be a cross like this. So we can also do a swap like this and to avoid these conditions. So after this observation, what is the total cost, or what is the minimum number of the move? What is the number of the move we need to do after we do a match? Then it should be the sum of all the delta x, which is always the same, no matter how you do the matching, plus the number of left lower red, the number of left lower red matches right upper yellow. And since this is always the same, this is always the same anytime, and the only things we need to do to minimize the number of the move is to minimize this part. And to do this, we can solve this in our not very hard, in an easy greedy algorithms. That is, you consider all the ones from all the red point, red grid from right to left, and then from up to down. And every time we match it with the lowest yellow that can match it. And if it is not, then we match it the most below yellow. And also there are many ways to do this, but this is not the important part. But anyway, after changing this problem into this type, we can solve it very easily in ON log type. Here the log may be from some data structures, or maybe a set in C++ or something else. But anyway, it is not that important. Yeah, and that's the first problem. Yeah. And also, you know that the swap operation is swappable, is invertible. So these two conditions, they are in fact the same conditions. And now we can only think of 1 in S that is at the left of 1 in T. And if not, we just swap S and T. Okay. And then comes to a very magical operations. So step 2 is somehow magic, but is reasonable, is that we can split the position from 1 to n into split, but maybe not split, but we can rearrange 1 to n into k times n over k grade. For example, if n is equals to 20 and k is equals to 5, then we can write the partitions 5 each column. Yeah. And then we can mark all the one in S to be red. For example, this is red and this is red. And also mark all the one in T to be yellow. Okay. After this rearrangement, what can we notice? For each one, if we want to, for each one in red, if we want to swap it, then we, as we talked about before, now we only think of one in S is at the left of one in T. So this means that S, each one in S will only be swapped to the right of it, or the number bigger of it, position bigger of it. So it can only be swapped to these positions. For example, if for this 13. And if we swap the red, one in red to the right upper corner, then what is the cost? Right upper corner. Then the cost should be the difference of their positions in x-axis, if we call this x-axis and call this y-axis. And that's the cost. And if we swap the one in S to the right lower quarter, then what is the cost? The cost is the difference in x-axis plus 1, right? You can check it. And what's the benefit of this? We'll find out that now we take the sum of all the one in S x-axis, not, it is delta x. All the delta x, this is the first part, and then plus the number of the match of red and yellow, that is from left to the this type of the matching. So this means that now the only goal we need to do is to find them as most pairs to match them from the left lower to the right upper. Because if we do so, then we can reduce the cost by 1. And if we do not do so, then the cost should be plus 1. And the delta x, this part is unavoidable. So this is always here, and we only need to minimize to maximize the number of matching of this type. And this can be solved in very easy greedy solutions. Regarding how to solve this using a greedy solutions, and we can think of the one in red from right to one in S from right to left and from upper to down. And every time we choose the most close yellow or most close one in T from in the y-axis and match them. And if not, then we have to choose the lowest yellow. And this is just a detailed work. That's the